When I was building my smallest 4K FPV drone, I needed to know which tiny props actually produce the most thrust. So I built a prop test bench, version 1. It worked, but it was manual, messy, and not accurate enough to really compare results. So now I'm building version 2, a proper test bench that fixes all of that. And with this setup, I finally want to test something special. 3D printed toroidal props. Do they actually work, or are they just a cool shape? Oh, and the app and the STL files for this will be available at the end of the video. Okay, version 1 had one big problem. I had to control the whole test by hand. And that's not just annoying, it's also inaccurate. I was literally trying to push the motor up to full throttle smoothly with my hand, and because of that, the curves never looked exactly the same between runs. They were always slightly different. But if you want to compare test results, you need repeatable routines. Like, the test has to run the same way every single time. So to make that possible, I need full automation, meaning no more manual input at all. The computer has to control everything, over and over, in the exact same way. But, how do you actually do that? Like, how do I automate the thing I'm doing by hand right here? So I'm expanding my app and making it take over motor control. And yeah, it turns out this is not as easy as I thought. At first, I assumed I could just control the ESC directly, the same way the flight controller does, because, I mean, something is controlling motor speed, right? So if the flight controller can do it, I should be able to do it from my app too. Long story short, I did get motor control working from my app, but not in the way I expected. Why that is, and what I had to do instead. I'll get back to that in a second, because there is no time to celebrate yet. I still had a lot of other stuff to build. My first version could only measure thrust, but there are so many other parameters that could matter too, like how fast is the motor actually spinning? What voltage is it seeing? How many amps are being pulled from the battery? How much power is it drawing right now? And stuff like that. But to get those values, you need to read the ESC while it's running. My original idea was to control and read the ESC through USB pass-through, because I wanted this test bench to work with basically any ESC you plug into it. But yeah, that's not really possible, so I had to use a bit of a workaround. I can now control the ESC as I wish, and retrieve live data such as voltage, current consumption, speed, and so on. And I can do this using a workaround, whereby I don't retrieve the data directly from the ESC, but via the flight controller. This is because it already has all the parameters I need. For version 1 of my prop test bench, I used an ESP32. Honestly, total overkill, and it's just way too big for this project. So I switched to an Arduino Nano, and yeah, I would regret that later. I had everything implemented, rewired, basically done on the Nano, and then I thought, wait, an OLED display would make this so much cooler. So I started digging through my Arduino box, found a little OLED, adjusted the code real quick, and then this pops up. Great. The Arduino Nano doesn't have enough memory, and at that moment I'm like, why did I ever move away from the ESP32? So I switched again, and this time to an ESP8266. That one should have enough memory for the display and all the other stuff. And it also gives me Wi-Fi on board, just in case that ever becomes useful in a future V3. And yeah, voila! And there's one more thing I haven't talked about yet. Version 1 used this load cell, and honestly, the only reason was that I already had it lying around. It's a load cell that can measure up to 5 kilograms, which sounds fine, right? Well, not really, because Whoop motors don't produce thrust anywhere near a kilogram. At first glance, that doesn't seem like a big deal, but let me explain for a second. A load cell works with strain gauges. When you put weight on it, the metal body bends just a tiny bit, and the resistance inside changes slightly. That tiny signal then goes into an analog to digital converter, like an HX711, which amplifies it and outputs a 24-bit value. Now here's the key point. Because we're only producing a few grams of thrust, I'm really just using maybe 1 or 2% of the full measurement range. The signal becomes extremely small, and suddenly vibrations and motor noise become huge in comparison. The readings start jumping around, and small differences between props or motors get lost really fast. So I switched to a 100-gram load cell. Because remember, the whole point is to test how whoop motors, props, and especially these toroidal props actually perform. My prototype version didn't even have a case. It was just thrown together quickly, and I literally fixed the load cell in place with a weight plate from the gym. So for version 2, I needed a proper enclosure, basically a box that holds all the electronics and keeps everything in place. So yeah, I pulled all the components into Fusion and just started sketching. This time I wanted something solid, a real test bench that only needs a USB cable and a power supply. So everything now fits into a clean, proper enclosure. For this test bench, I specifically designed TPU feet, because they give more grip and keep the box from sliding around. But for my Voron Zero, those tiny TPU feet were basically the final boss. And honestly, they drove me crazy. I went through so many iterations. I redesigned it, printed it again, changed the orientation, and printed it again and again. But I did find a solution. I'll get to that in a second, because at some point I suddenly felt like this thing absolutely needed one of those fancy emergency stop buttons. I don't know why, but I really wanted one. So I ordered it and waited for it to arrive. And then I realized, wow, these things are way bigger than I thought. And my test station is way smaller than I thought. And the way I originally wanted to mount it, it would actually sit right in the airflow and potentially mess with the test results. But yeah, giving up the emergency stop button was not an option anymore. So I had to rethink everything. The problem was, I also didn't want to make the enclosure unnecessarily big, because it still needs to be printable on a Voron Zero. In the end, this is the design I went with. The emergency stop is now mounted slightly off to the side and out of the airflow. That way you can quickly hit the button if something weird happens and instantly cut power to the ESC. How many times do you think I'll use this button? Drop a guess in the comments. During assembly, I did improvise a little here and there. For example, right here. I mean, one screw is probably good enough, hopefully. And the feet had to be glued in place. My original plan was for them to just snap in and hold themselves, but yeah, that didn't really work out. By the way, I also learned that pressing too hard on the all-day display is not a great idea, so I had to order a new one, because that was my last spare, and I adjusted the design so that hopefully won't happen again. I'll spare you the many hours of small changes in Fusion, and instead, let me introduce Prop Bench V2. Now, if you want to compare test results properly, you need identical test scenarios, so I built those directly into the app. The first test is the max thrust test. It spins the prop up to maximum speed 3 times in a row, and then outputs the average value. The second test measures maximum acceleration. The app records how long the prop takes to reach full speed. The third test is something pretty special. It measures the efficiency of the motor and prop combination by setting a minimum thrust target. So basically, you tell the system how much thrust you want, and it figures out how efficiently that setup can produce it. That way, you can find out which combination works most efficiently within a specific thrust range. For a quick comparison, the app also gives you a high score value after each test. Now that the test bench and the app are finally done, we can get back to the original idea. How do these 3D printed toroidal props actually perform on the bench? Back then, this test bench would have been absolute gold for my 3D printed long-range build. So I'm finally going to redo that test properly. That means I'm using the same motors from back then, the same lithium cell, and the same props I originally flew. And then I'm going to let that setup compete against the bi-blade toroidal props. For another test, I'll use the smallest brushless motors, a high-voltage LiPo, and a tri-blade gem fan prop. These are the same motors and battery from my smallest 4K drone build. And then I'll put that setup up against tri-blade toroidal props in the same size. Let's see how they compare. Alright, first up is the test with the motors and the battery from my long-range build. First, we measure the maximum thrust 3 times in a row, so we can calculate an average. Between each test, there's a short pause so the battery can recover. Okay, now we're testing the acceleration. I'll come back to that later because few things stood out to me. For the efficiency test, I chose a target of 10 grams. First, the app figures out how much throttle is needed to reach that thrust. Then it holds that throttle level for 10 seconds and measures how much power is required to maintain it. And this right here is our first score result. And now we're doing a test run with the mini motors. Now, of course, this comparison isn't completely fair. The motors are much smaller and the props are smaller as well. On the other hand, a high voltage LiPo can deliver more current than a lithium-ion cell, and both setups are meant for very different purposes. One is more like a sprinter and the other one is more like a marathon runner. For me, what's really interesting is the different classes that I can measure with the prop bench. So here as well, we're running the full test again, using the same 10-gram target for the efficiency test to keep the conditions consistent. Honestly, I already find these results really interesting. You can clearly see how much more efficient a lower kV motor with a larger prop is. This test bench opens up so many possibilities for me now. But alright, let's get to the 3D printed toroidal props. Let me know down in the comments what kind of test scenarios you'd like to see. When designing the toroidal props, I try to get as close as possible to the regular props. The prop size is identical, but there are a lot of different parameters when it comes to designing toroidals. I'll spare you all the in-between steps and just show you the final versions. But I'll tell you one thing, printing these things was a nightmare, especially when you try to print props this small. And since I've been working on this project for about 3 months now, my P2S finally arrived. And honestly, this is the best result I was able to get. Okay, so when you print propellers like this, they almost never come out perfectly balanced. And since I don't have a proper prop balancing tool, I had to improvise a little. It was pretty tedious, but it actually improves the performance a lot. My expectations were honestly pretty low. Whenever I think about 3D printed props, I immediately think about them exploding mid-air, especially with high RPM motors like Whoop motors. So yeah, safety first. I really don't trust these things. Okay, this is already blowing my expectations because I honestly thought this thing would just explode right away. The results from the 75mm toroidal prop actually surprised me. They're not bad at all. I mean, the 3D printed toroidal prop even beats the 35mm GemFem prop in every category, but the 35mm props just don't work at all. During the max thrust test, I already realized the full test was going to fail. The prop couldn't even reach 10 grams of thrust, so I knew the app wouldn't produce a result. I've fixed that in the app by now, so the test will still run to completion even if it doesn't reach the target. But for a quick fix in that moment, I had to lower the efficiency test to 5 grams and run it again. The test did finish after that, but the result is pretty disappointing. Other than a lot of noise and maybe a tiny bit of lift, these props basically didn't work at all. I based the design on the GemFem props and calculated the pitch and the blade size accordingly, but the result is pretty disappointing. The toroidal prop barely produces any thrust. My guess is that there's something wrong with the design here. So if you have any idea what the problem might be, let me know down in the comments. And honestly, I think the acceleration test is kind of flawed. That's why I only weighted it at about 5% in the overall score. My guess is that the sampling rate just with the app isn't high enough, and that I probably need to run the calculation directly on the microcontroller. But I'd actually be curious to hear what you think. Let me know in the comments. Building this thing was honestly a lot of fun. I spent months working on it, constantly improving little details here and there, and honestly, I could have kept refining it for a lot longer. But then the video would have taken even longer to come out. The story of the prop bench V2 is definitely not over yet, and if you don't want to miss what comes next, now would be a good time to subscribe. Alright guys, and with that, I'm keeping my promise. You'll find all the links to the files, the materials list and the app, either on my Patreon page or down in the description below. Everything is completely free, but I'd really appreciate any support. My goal is to reach 100,000 subscribers. So if you enjoyed this video and want to support the work, leave a like, comment prop bench, hype up the video, and consider subscribing. And hey, if anyone's on Windows, could you test if the app runs properly and let me know? I'll see you in the next video.